Namaste and welcome back to the Data Structures and Algorithms classes. We were discussing about the bitwise operators, and out of all the different operators, we have discussed all these operators, but we have not discussed about the right shift and the triple right shift operators, right? And also the negation operator. Now, you must be wondering, what does this right shift and triple right shift do? Well, it's very interesting. Let's have a look, okay? Now, let us assume, guys, like this, right? I have an integer variable a whose value happens to be 5, right? And what I will do is, on a, I'm going to perform right shift operation once I'm going to perform. Now, if in case we are speaking about Java specifically, you guys know that the size of an integer variable in Java is 4 bytes. So 1, 2, 3 and 4. 4 bytes I have. You're able to think. Now the thing is, ultimately, you know 5 will be converted into its binary form. So 5 in binary in just 8 bits looks like this. The last 3 bits is 1, 0, 1. Of course, all these other bits will be filled with zeros. I hope you're able to think. Will be filled with zeros. Great. Now, when you say right shift, obviously you're saying every bit must be shifted one position to its right. So if I start shifting it, you can see, let's start from the rightmost bit, one position, one position, one position. I'm showing you arrow marks everywhere, right? Clearly you can notice that if you do right shift once, from the right side, you will lose 1 bit. If you are going to right shift it twice, you would have lost 2 bits. 3 times means from the right side you would have lost 3 bits. Naturally, common sense, that is how it works. Anyways, right now I will lose that last bit, that will go away, but all other bits will come and sit in the respective position, which means the last 2 bits is going to be 1 and 0, and then you can notice everywhere zeros will get filled, but here one void is there. What will get filled here is the question, because here there is nothing. Now please understand, right shift operators will automatically fill this position, but the question is, what will it fill it with? Now you must understand that right shift operator is also called as the signed right shift. It is also called as the signed right shift, or it is also called as the arithmetic right shift. Now what does it mean? What it does is, it will look at the original value and it will see what is its most significant bit. And what was its most significant bit? 0. 0 means it is a positive number. Whatever was the MSB, that same MSB will be used as a filler, guys. Which means like this, that 0 will be used to fill. If there were 2 empty positions, the same 0 will be used to fill the 2 empty positions. If there were 3 empty positions, same 0 would have been used to fill the same empty position, or in other words, the MSB is used as the fillers in the right shift operation. I hope you're able to think. Any confusion till here? Great. Now that it is filled, obviously all you have to now do is convert it back into decimal to understand what this value would be. So all these are anyway zeros. So the only one you have is 2 to the power 1, and 2 to the power 1 is 2. I hope you're able to think. So if in case I take 5 and if in case I right shift it once, I should be getting 2. I hope you're able to think. Will this really work? We will write some code and explore it later. But just to show you, let us assume I will reset this. It is still a equal to 5 only. And you know a equal to 5 looks something like this. Now, I'm going to right shift a by 2 times. So, it is 1, 0, 1. Now, the 0, 1 will be lost if you right shift. See, I'm putting arrows. If you right shift 2 times, you know that the last 2 bits will be lost. So, it is 1, 0, 1. This 0, 1 will be lost. 1 is going to come to the last bit, and rest everything will come to its own position as I'm showing. These last 2 bits will be empty. If these last 2 bits are empty, then what will be filled there? Right shift operator will always use the most significant bit as the filler, and the most significant bit is 0 because it is positive, and the same 0 is propagated. As you can see, zeros got filled. How we're able to think? And obviously there is only a single one, and that is at 2 to the power 0th position. 2 to the power 0 is 1, which means if I right shift 5 by 2 times, I am going to get 1. I hope you're able to think. Or in a way, if you look at it, if I right shifted 5 once, it is like dividing it by 2, right? But floor division. If I right shift it by 2 positions or 2 times, then it is like dividing by 2 once and then dividing that again by 2 once more, or dividing by 4, you can say. So technically 1 only you will get if you floor divide it. I hope you're able to think. So the way left shift was for multiplying by 2, right shift can be visualized as dividing by 2. Any confusion till this point of time? I hope it is clear to everyone. But the larger question could be, how does the triple right shift work? Let me show you. Before we proceed and understand the triple right shift operation, let us first understand how right shift works on negative numbers. Assume I have the same integer variable a, but this time it has -5 as the value inside it. I am going to right shift a by once. Now what is going to happen is the bigger question. Now all of you know negative numbers are stored inside the memory in the form of 2's complement. I have already explained this. How do you find the 2's complement? First find the binary version of the positive number. Now you know +5 looks like this, right? To take 2's complement, first you must take 1's complement. If you do 1's complement, you will have to flip all the bits, and if I flip all the bits, this is how it looks like. After which, if you want 2's complement, you must add 1 to it. If you add 1 to it using binary arithmetic, finally this is what you will get, and ultimately you can see the last 3 bits is 0, 1 and 1. Any confusion till here? Now that is what is stored inside this. So it is stored inside this. So last 3 bits is 0, 1, 1. I hope everybody understood. Next what? Now what I am doing is right shift. By how many positions? 1 position. So I am showing the arrow marks. Now I am just transferring all the bits to their respective positions. You can see there is a void. If you right shift by once, you will use the last bit here. Obviously in the first bit here there will be a void. Now what we are doing is signed right shift, right? It's also called a signed right shift. Signed right shift, why it is called as is because it will fill the void. The fillers that it will provide is always equal to the MSB. And what is the MSB here? 1. Why? Because it's a negative number. All of you know that, which means the same one is going to get filled here. If there were 2 voids, then the same one only would have filled it. I hope you're able to think. I think that everybody has understood by now. So 1 fills it. Any confusion till here? Wonderful. Now, this is the value of right shifting -5 by 1. Now foolishly what people will do is they will try to convert this directly into decimal and they will end up in a wrong value. No, you must not do that. You must not directly convert into decimal, because imagine every value is 1. This is 2 to the power 31. Imagine if you add all of this, you will get like that highest range number of an integer value, right? We don't want that. So what should you do? What you must do is very simple, guys. You must now first undo the 2's complement that you have performed on this and only then convert it into decimal and apply a negative sign. Sir, how do I undo the 2's complement? What you did, do it in the reverse manner. For 2's complement, first you did 1's complement, then you added 1 to it. Now reverse you go, which means first I added 1, isn't it? Now I will subtract 1 from it, -1. If I subtract 1 from it, this is how it will look. Now 1's complement you remove, 1's complement you remove, which means you have to flip the bits. If I flip the bits, this is how it will look. And you can see the last 3 bits is 0, 1, 1. Any confusion till this point of time? 0, 1, 1. Now, if in case you are going to convert this into decimal, then that is 2 to the power 0 and that is 2 to the power 1. 2 to the power 1 is 2, 2 to the power 0 is 1. If I add both of them, it is 3. But you must not just tell 3, you must attach a negative sign, which means it is -3. I hope you're able to think, which means -5 right shifted once is -3. And why it is -3? I hope everybody got a clear cut picture. I hope you're able to think, right? Now, before we go and look at the triple right shift operation, let us first see whether really in code this is how things work. Alright, let's write some code. Simple, I'll just tell system.out.println. and directly I will just tell 5, right shift it once. Okay, let's see what we will get. If I execute it, technically you should get 2 because it's technically 5 divided by 2, which is around 2.5 something, but floor division means if you round it towards the floor, it is 2. So I told you it's equivalent to divided by 2. If I do twice, it is equivalent to dividing it by 4, which means I should get 1, right? See, it works. Great. However, what if I make it as -5 and I make that side as 1, because that is the example that we did, right? So if in case you observed it, if I execute it, this is what we should be getting, -3. Perfectly it works. Perfectly it works. So I hope you are convinced that how to approach it, right? See, now you must understand that whenever you do that reverse of the 2's complement, right, to finally create the decimal number, that should only be done whenever the MSB is 1. Whenever the MSB is 1, it means it's a negative number. Now, if you have MSB 1 and it is a negative number, if you directly just convert it into decimal, then imagine you have to take 2 to the power of the MSB, which is 2 to the power 31. It will be a mistake. You will never get the actual value. So you must undo the 2's complement by first subtracting 1, which is undoing the 2's complement, and then flipping the bits, which is undoing the 1's complement, and then you have to take its decimal value and then attach a minus sign to it. I hope everybody understood, right? Great. Now what is this triple shift operator all about? Let's explore. Now let's understand triple right shift. Now a disclaimer. Please understand, those of you who are learning Python, triple right shift is not supported in Python. But it does not harm you to know how this works, because it is not about whether you are a Java or developer or a Python developer. Ultimately, if you are going to survive in the IT industry and make it big in the IT industry, you are going to work on multiple programming languages throughout your life. So knowing about multiple programming languages is always a strength that you possess, right? So now please understand. Let us start with int a equal to 5. Now I am going to triple shift a by 1 position. Now don't think triple shift means some 3 times shifting will happen. No, no, no. Triple right shift works like just right shift. However, there is a fundamental difference. First of all, triple right shift is called as unsigned right shift or logical right shift. Unsigned right shift or logical right shift. Now what does this even mean? You know, +5 in binary looks like this. And ultimately, just like a normal right shift, because it will right shift by once, even triple right shift will right shift every digit by once, and I'm showing the arrow marks, and automatically digits will be filled. So out of this 1, 0, 1, 1 will be lost, and hence you will have 1 and 0 here. There is a void here. Now please understand, how was your right shift working? It saw what was the most significant bit, used that as a filler. But you must understand, this is the primary difference between right shift and triple right shift, which is triple right shift does not care about the MSB. Whether the MSB is 0 or whether the MSB is 1, triple right shift is always going to use 0 as the filler, which means it is going to fill a 0 here. It is just pure coincidence that the MSB here is 0, MSB here also is 0. It's not that this was used here. If it was 1 also, this would have been 0. That is what I'm trying to say. Irrespective of the MSB, 0 is always going to be the filler, right? So this is what ultimately we have. And this is, see, look at the most significant bit, it is 0. If the most significant bit is 0, it means it's a positive number. You just have to directly convert it. You just have to directly convert it. If I directly convert it, it is just 1 and 0 here. So this is nothing but 2 to the power 1, which is 2. So 5 right shifted ones is 2, right? Triple right shift 1 is 2. 5 right shifted ones is also 2, which means there is no difference between triple right shift and right shift when it comes to positive numbers. I hope you're able to see there is no difference. There will not be any difference. But the true difference arises when it becomes a negative number, my dear friends. Let us assume it was -5. I'm clearing these bits. You know that -5, initially this is the positive 5, then you have to take 1's complement, flip the bits, then you have to take 2's complement by adding 1, and then this is what you will get. Ultimately that is what will be stored, right? So here what is going to happen is I'm going to right shift. If I right shift, this bit will be lost. This bit will be lost. If this bit is lost, then what will be stored here? All the bits are going to be right shifted, and ultimately I'm going to have one missing bit here. Now, if it was normal right shift, the most significant bit would have been used as the filler. But this is unsigned right shift or triple right shift or logical right shift. It does not care about the MSB. If there are empty spaces, the fillers are always going to be 0, which means 0 is going to be added. Any confusion till here? If 0 is added, then finally this is the value that you have. You have a lot of ones here, but the most significant bit is 0. Now, those of you who understood the previous example where I used right shift on negative will now try to undo the 2's complement. That is where you will make a mistake. Undoing of 2's complement must only be done if the most significant bit happens to be 1 or it is a negative number. But if the most significant bit is 0, my dear friends, this is a positive number. No need to undo any 2's complement. Directly you have to convert. So I'm just putting the power of 2's, and you can see even since this bit is 1, the power of 2 till 2 to the power 30 you have to take. So if in case I add everything up, this is the value that you're going to get. Huge value, huge value. And it's a positive value. So imagine if I right shift -5 by 1 position, it has become a positive number. So did you understand why it's called unsigned? Sign is ignored because sign is always going to be 0. I hope you're able to think. Sign is always going to be 0, whether it is positive number or negative number for triple right shift. And see such a big value you have got. I hope you understood. Really, will this happen? Let's write some code and explore. Let's see whether the right shift operator works, the triple right shift operator works the way it's supposed to work. I'll just tell this out. And I will take 5. And I will right shift it, triple right shift once. So clearly this should give us the same as your normal right shift, right? Because it's a positive value. So if I execute it, I should be getting 2, and yes, I have got it. So no difference. I told you for positive numbers, triple right shift and your right shift work in the same way. Now if in case I go and I were to make that as -5, this is where the true difference comes into the picture, right? Where if for the right shift operation, we got a negative number. But because this is unsigned right shift, you should be getting a positive number. Really, will this happen? Watch it. Hope you're able to think. So perfectly it works. I hope you're able to think. Anyways, now let me just quickly go and show you in a tabular format what is the difference between right shift and triple right shift. Let me quickly show you the difference between right shift and triple right shift, right? The first difference is in the names. So right shift is known as arithmetic right shift, or it is also known as signed right shift. Whereas triple right shift is known as your logical right shift or unsigned right shift. The second major difference you know is that in right shift, it is always the MSB which is used as the filler, but in your triple right shift, 0 is always used as the filler. When it comes to the third and final difference, in the normal right shift, the sign of the number is preserved, but in your triple right shift, the sign is not preserved. And I hope I've demonstrated each of them and you've understood it clearly. Alright, now the last bitwise operator I want to show you is the negation operator, which looks like this tilde symbol, right? Now, what does this negation do? As the name tells, it negates the number that is given to you. Now, how does this work? Listen, and I'm explaining to you carefully. Now, let me take a value 2, for example. 2 in binary, you know, is 8, basically 6 zeros and 1 and 0 in the end. Now, if in case I do negation of 2, how negation operator works is it flips the bits, right? It's like 1's complement. So when it flips all the bits, all zeros become 1's and all 1's become zeros. I hope you're able to think. Now you can see that is the negation of 2 in binary. Now if you want to represent it in decimal, then conversion must happen. Now you know whenever the MSB is 1 and when you convert it into decimal, it is very important that you undo the 2's complement. And undo the 2's complement begins by subtracting 1, in which case that is what I will get. Then I have to flip the bits, in which case that is what I will get. And if in case then I convert it into decimal, I will get 3 and then I will attach a negative value to it. So it is minus 3. So negation of 2 is minus 3. I hope you are able to think. What about negative numbers? Very simple. Now let us assume I want minus 2 to be represented. You know minus 2. First of all, 2's complement of 2 you should take, right? So 2 is this. If I do 1's complement, it is this. If in case I add 1 to it, which is 2's complement, that is what I will get. This is minus 2 in binary. Now you are telling negation of minus 2, which means it will just flip the bits. All 1's become 0s, all 0s become 1's, right? Now you can see MSB is 0, which means it's a positive value. Direct conversion. The last bit is 1, which means 2 to the power 0, which is nothing but 1. So negation of minus 2 is 1, right? Also, my dear friends, there is a very simple formula that is given without directly doing all this, you can figure out what will be the negation in decimal, right? So the formula goes like this. Negation of n is equal to minus of within brackets n plus 1, right? Does this work? Watch it. Negation of positive 2 is minus 2 plus 1, which is nothing but minus 3. Negation of minus 2 is nothing but minus 2 plus 1, which is nothing but 1. I hope you're able to think. Matches. So the formula is also there. How it works in binary is also clear to all of you. Please understand. Next, what I want to do is I want to show you all the bitwise operators that we have discussed. We have discussed all these bitwise operators and each and every one of them, how it works in the memory in terms of how the conversions happens, etc. We have discussed it in great detail. But now the larger question is, where do we use them practically? Well, for that, we will have to solve n number of programs, and that is what we are going to do next.